I'm going to be working here the homework for 8.4. This is the other convergence tests, and we're starting out with number 3. So we have an alternating series, and we want to recognize that we can rewrite this in sigma notation first. So we have a sum n equals 1 to infinity. Noticing that it's alternating starting with a positive term, so I'm going to use negative 1 to the n plus 1. That should start it out with a positive. I notice all my numerators are 4. I notice that my denominators are counting numbers, 7, 8, 9, 10, 11. So they're just counting starting with 7, so I need to use n plus 6. So this is my series formula, and since it's an alternating series, I'm going to identify what b sub n is. And then I'm going to use the alternating series test on this problem to try and figure out what this converges, if this converges or diverges. So make sure I'm doing this yet. So here are the things I want to show. The first thing, I need to show that b sub n is greater than b sub n plus 1. And so that means it's decreasing. Well, b sub n is 4 over n plus 6. b sub n plus 1 is 4 over n plus 1 plus 6. So that's really 4 over n plus 6 must be greater than 4 over n plus 7. And if I clean this up and move things around, I should get 4 times n plus 7 is greater than 4 times n plus 6. And distributing 4n plus 28 is greater than 4n plus 24. Subtracting 4n on both sides, I get this, 28 greater than 24. That is true. So I've shown the first condition for the alternating series test. Now, all I need to show is that the limit as n goes to infinity of b sub n goes to 0. So let me show that now. So take the limit as n goes to infinity of the b sub n part, which is this. This needs to go to 0, which in fact it does, because I have a fixed number over something that gets infinite. That goes to 0. So by the alternating series test, that sum, this series converges. All right, let's take a look at number 5. Or sorry, number 4. Number 4 is kind of interesting because something different happens in this series after you get it into the sigma notation. Let's just set it up here real quick. So number 4, it's negative 3 over 4 plus 5 over 5 minus 7 over 6 plus, just make sure I'm doing this, 9 over 7 minus 11 over 8 plus dot, 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 dot. So this again is an alternating series. I can pick up on the pattern pretty easily here. I'm getting a negative first, then positive, so I'm going to use negative 1 to the n. And then my numerators are all odd numbers, starting with 3. So I use 2n plus 1. And then my denominators are just counting numbers starting with 4, so n plus 3. And I could go through the alternating series test and figure out what this is doing. But if I do the nth term test, and I take a look at just this part for now, the limit as n goes to infinity of 2n plus 1 over n plus 3, this you would have to use L'Hopital's rule on. You would get 2 over 1. So you just get 2. That's not equal to 0. And remember, if your n-term test is something other than 0, it's going to diverge. The only thing we need to figure out is how does the negative 1 have an effect on this? And all the negative 1 does is makes it flip back and forth with signs. So when you look at your series, right, it's jumping back and forth between numbers that are getting closer to 2 and negative 2. And by the definition, by the end-term test, this will automatically diverge. So we're pretty much done. And I'm going to stop writing the summary here because of time constraints. I'm just going to verbally say what the conclusion is. So here we would say it diverges by the end-term test. All right, 5 is very similar to number 3, so I'm not going to do that. Number 6, I did in class, so I'm not going to do that one. Number 7 is very similar to number 4, and so I'm going to do number 8. So we have sum n equals 1 to infinity of negative 1 to the n cosine pi over n. This is kind of a weird one because we've never really seen that trig function in here in our series before. But let's just figure out what's happening as n gets big here. As n gets big, it flips back and forth, right? It's changing signs. And then as n gets big here, this is pi over a big number. That goes to 0. And cosine of 0 is 1. And that's a problem because the nth term test, again, if we just run the nth term test on this, the limit as n goes to infinity of cosine of pi over n, we know that that's going to be 1. And that's not 0. And so we know that this should diverge, even though this is switching back and forth, negative, positive, negative. Since this part doesn't go to 0, there's no way that this sum can converge. So again, divergence by the nth term test. All right, number 9. This is where things start getting a little interesting. So they give you a series. Negative 1 to the n plus 1 over n to the 6th. It says, show that it's convergent. How many terms of the series do we need in order to find it, the sum to the indicated accuracy? So they want an error of less than 0.000, how many zeros are there? 1, 2, 3, 4. 0, 5. They want our accuracy to be within that error. So we know we can never add this up forever. If this converges, we want to figure out how many of these we would need to add up to get within that close of the true sum. So first let's confirm that it converges. So to do that, I think what I'll do, I could do the alternating series test here, but how about we look at this? Let's look at the absolute value of this. All right, the absolute value of that, the negative 1 doesn't matter anymore. It's always a positive 1. The n to the 6th absolute value is just n to the 6th. And this is a p-series. And p is 6, which is greater than 1, which means it converges. So by the last thing on your sheet of tests, we have that if the absolute value of the series converges, then which is this. If this converges, then that has to converge. So my conclusion is that it does converge. Now I need to figure out how many of these I should add up in order to get the desired accuracy. So from class, what I said is that the true sum minus the partial sum has to be less than b sub k plus 1. And so what we want is, this is the error right here, okay? The error, we know that by the theorem it has to be less than b sub k plus 1. But we want that to be less than 0.00005. So I need to figure out what b sub k is. So remember that you have to rewrite this with the negative 1 part peeled off, and then 1 over n to the 6th. That is the piece that is your b sub k. All or I should say b sub n. It's b sub n. But we are going to plug k plus 1 into that. So I want 1 over k plus 1 to the 6th power to be less than 0.00005. And there's several ways you could do this. You could try and solve for k here with an inequality, but we can just pick some numbers for k and see if it works. So I'm going to get my calculator out. I'm going to start trying various values of k until I make that inequality true. So let me try starting with, let's try k equals 1, see what happens. So if k equals 1, I get 1 over 1 plus 1 to the 6th. And my question is whether or not that's less than, well, I'll ask the question. Let me figure out what this is on my calculator. But my question will be, is it less than this? So I get to my calculator. This is 1 over 2 to the 6th power. So 1 divided by 2 to the 6th. This is 0.015625. Is that less than 0.00005? No, it's not. So k equals 1 was not enough. That means when I'm taking that sum, starting at n equals 1, if I try and stop at 1, which means I just take the first piece, the first number, and don't add anything else to it, it's not going to be close enough to the true sum. Well, not as close as I want it to be. So I need to go with the bigger k. So if k is equal to 2, then I get 1 over 2 plus 1 to the 6th. Let's see what that is. So that's going to be 1 divided by 3 to the 6th. This is equal to 0.001372-ish, somewhere around there. And again, that is not less than 0.00005. So I've got to go again. Try something else. And we're looking for the smallest k. Of course, I could let k equal 10 and it would work, but I'm trying to find the smallest k that's going to work. So k is 3, 1 over 3 plus 1 to the 6th. Let's see, that's 1 over 4 to the 6th. I get 0.000244. So that's still not less than this. So let me try k equals 4. So if I do that, it's going to be 1 over 5 to the 6th. When I do this 1 over 5 to the 6th, I get 0.000064. Let me see. 1, 2, 3, 4, 5. Yes, and that is still not less than this. Just a little bit bigger, right? They all have 4 zeros. This is a 6, that's a 5, so this is bigger than this. And so I think it would be safe to say if I use 5, it'll work. Let me just check it. K is 5, I get 1 over 6 to the 6th. 1 over 6 to the 6th. I get 0.0000. Doesn't work. 214, something like that. And that is less than 0.00005 because this number is smaller than this number. So I would have to do the sum out to k equals 5 in order for this to be close enough to the true sum or within this much of the true sum. So this is what, tenths, hundredths, thousandths, 10,000ths, 100,000ths. So I would be within 5 100,000ths of the true sum if I sum that series out to 5. I hope that makes sense. All right, let's do the next problem. So we have sum n equals 1 to infinity of -1 to the n times 1 over n times 5 to the n. So on this one, I already split it up from what it looks like in the book. Does it converge or diverge? Well, I can use any test I want here. And since I see an exponent, I'm actually going to use the ratio test. Because anytime I see exponents, I like to try that first. So with the ratio test, I'm going to set up a limit as n goes to infinity of a sub n plus 1 over a sub n. And that this whole thing is a sub n. So this is the limit as n goes to infinity of, now I plug n plus 1 into all the n's. So negative 1 to the n plus 1 times 1 over n plus 1, 5 to the n plus 1, over, now a sub n, which is just negative 1 to the n times 1 over n times 5 to the n. Now, when I take the absolute value of this, the absolute value of negative 1 to any power, that's going to be a 1 no matter what. That's going to be a 1 no matter what. So this turns into limit n goes to infinity of absolute value. So I'm ignoring these now, and I have this over this, right? So these are really pretty much gone. So I have a fraction over a fraction. So what I'm going to do is I'm going to take this and I'm going to flip it. And when I flip it, this is what I get. N on top with 5 to the n, and below it will be n plus 1 times 5 to the n plus 1. Now at this point, I take my limit as n goes to infinity, and I notice that on the bottom, I can rewrite 5 to the n plus 1 as 5 to the n times 5. And that's a great thing, because these 5 to the n's will cancel. And so I'm left with, that becomes the limit as n goes to infinity of, let's see, I have an n on top. On the bottom, I have an n plus 1 times 5. I can distribute the 5 through there, 5n plus 5. And right now, if I take this limit, I get infinity over infinity. I do L'Hopital one time on that, and this will become 1/5. And that's definitely less than 1, because the ratio test says you have to check if this ratio is greater than 1 or less than 1. If it's less than 1, it converges. So it is a convergent alternating series. Now I have to again go through that process, try and find a k to get the error on this thing to be less than 0.0001. So I want my error to be less than 0.0001, which basically means I want my b sub k plus 1 to be less than 0.0001. Now, on this problem, b sub n is this piece. So b sub k plus 1 would be 1 over k plus 1, 5 to the k plus 1. I need that less than 0.0001. And now, again, I'll try some different values of k. So for k equals 1, I'm going to get out my calculator. I'm computing 1 over 1 plus 1, 5 to the 1 plus 1, which is 1 over 2 times 5 squared. So let's see what this is. 5, that's 1/50th. Duh. This is 0.02, and that is not less than this. So I try k as 2. For that, I get, let's see, 2 plus 1 is 3. 2 plus 1 is 3. So now I need to do 5 cubed. So 5 times 5 is 25. times 5 again is 125. 125 times 3, 375. So I'm doing 1 over 375 is 0.0026 repeating. That's still not less than this. So I go to 3. K is 3. 1 over 4 times 5 to the 4th. So one over 2,500 is equal to 0.0004. I'm getting close. 0.0001. So I need to go probably just one more. K is 4. 1 over 5 times 5 to the 5. And this is actually 1 over 5 to the 6th. And that's going to be 0.000064. So you can see it got pretty small. So I'm definitely less than this now. So K would be 4. If I take the 4th partial sum, then I'll be in business. Now, again, let me reiterate what this is that we're doing, because I think this can be a little confusing for a student. We have this alternating series. It was -1 to the n times 1 over n times 5 to the n. We know it converges, so we know that that adds up to a number. It gets closer and closer and closer to a number as you let n go to infinity. But we can never add this up forever. What we just determined is that if you add this up from n equals 1 to 4, which is a finite sum now, I mean, you could actually add this up. First you plug in 1, get that number, then 2, then 3, then 4. You stop at 4. Whatever this answer is, okay, I'll call it S sub 4. And if this up here, since it converges, if I call that capital S, then what we're saying is the error is less than this. So the true sum minus our approximation is guaranteed to be less than this number. And so if someone wants me to get this close to the true answer, I can do it. If someone wants me to get even closer, maybe adds more zeros in here, I can get closer, but I'm probably going to have to go further out into the sum. So it's a way of estimating a sum, and very, very useful for us. It helps us avoid having to think about adding something up forever. All right, let's look at the next one. 11. Sum n equals 0 to infinity of -1 to the n over 10 to the n times n factorial. I'm definitely using the ratio test here. So let's go with ratio. So limit n goes to infinity. And then what I'm going to do is plug n plus 1 into this first. And then divide that by just that series itself without replacing the n. There we go. And now I know that these aren't going to matter. Those are basically 1s because I'm going to do an absolute value. So I don't have to consider them at all. And then the other thing is, since this is a fraction, that's really a 1 on top. And this is a fraction with a 1 on top. I can flip this one up like this. So it'll look like this. It'll be 10 to the n times n factorial on top. That's this one up here. And then on the bottom, I have 10 to the n plus 1, which I'm going to write as 10 to the n times 10. And then n plus 1 factorial, which I'm going to write as n plus 1 times n factorial. So I'm just using properties of exponents here and the property of factorials. And I do that because these n factorials will cancel, the 10 to the n's will cancel, and what you're left with is the limit as n goes to infinity, the absolute value of 1 over, and this is just 10n plus 10, and that goes to 0, which is definitely less than 1. Therefore, this alternating series converges. Now, again, I've got to figure out how far I've got to go out to get an estimation. So how close do I want this to be? Oh my goodness. 1, 2, 3, 4, 5 zeros. I want my error to be less than this. Now, my b sub n, which I erased here, was just the part of it without the alternating negative. So it's just a 1 over 10 to the n factorial. So I know that this error, I can do b sub k plus 1. I need that to be less than this. And now I figure out what b sub k plus 1 is, which is 1 over 10 to the k plus 1 times k plus 1 factorial. I need that to be less than this. And now I try some values of k. Let me start with 2, okay? Just guessing that 1's not going to be enough. You know what? Let me start with 3. 4? Let's start with 4. I just don't want to spend too much time on this. So if I do that, I'm going to be computing 1 over, let's see, 10 to the 5th times, let's see, 4 goes in here, 5 factorial, which equals now, I'm going to have to do this on my calculator, 1 over 10, 1 divided by, I think I went too far. 1, 2, 3, 4, 5, 6, 7, 8, something like this. That's a little too far. So let me try 3. 3 would give me 1 over 10 to the 4 times 4 factorial. So 1 divided by 10 to the 4 times 4 times 3 times 2. This is 0.0000416, and that works. That's less than this, just barely. So with k being 3, that should work. Now, we have to be a little bit careful on this one, because this one, if you look back on the original one, the sum started at 0 instead of 1 to infinity of negative 1 to the n times 1 over 10 to the n times n factorial. So what we just got from that says that we should go out to k equals 3. So let me just look at something real quick here. What number is this? 11. So what this was saying was that if n was, let's see, 3, if n was 4, so if this number is a 4, right, then that one would be big enough. this would be a big enough k for this to work. So I'm trying to think of how I can explain this easily. Let me do it this way. Okay, this will make things the easiest, and this leads into what's coming later. This is the original series. Everything we did here works just fine when n here is 1. But if n isn't 1, then it doesn't, we're off a little bit. It's hard to see, but we'll be off on the theorem. So what I'd like to do, this is the first time I've ever done this, I'd like to change this to a 1 to infinity instead of a 0 to infinity. So how do I do that? Well, I look over here, and I just look at it like a little equation. How could I take n equals 0 and rewrite it where it becomes n equals 1? Well, what I'll do is I will replace this n with n minus 1 equals 0. And then if you just move the 1 to the other side, it becomes n equals 1. So the big thing is that to change your index from n equals 0 to 1, what you have to do is you have to replace all your n's with n minus 1's. So watch. I will take this series right here, everything. Everywhere I see an n, I'm going to replace with n minus 1. Everywhere. Sum n minus 1 equals 0 to infinity, negative 1 to the, let's see, there's an n, so n minus 1. And then here, 1 over 10 to the n minus 1 times n minus 1 factorial. Like that. And now, remember, this right here really just means n is 1. What I've done is I've converted this whole thing over to a brand new series. It creates the same exact thing that this does. If I plug in 0 here, I'll get the same thing as what I get when I plug 1 in here. But the reason I need this is because I want this sum right here, this k right here, to be 3. This number right here to be 4, right? I want this number right here to be 4 for this to work, 10 to the 4th and 4 factorial. In order for that to happen, I actually need this number up here to be a 5. So when I plug in 5 here, I get 4, and then I get 4 here. Now, I know this is confusing, but because it started at 0, that throws it off a little bit on the estimation theorem. So my suggestion is if you ever see a series that starts at 0, when you go to try and find the error, convert it over to n equals 1 after you've figured this out, and then figure out what that number was and see how you would get it here. So our answer is k is 5, not 3. We need a 5 here in order to make that a 4. All right. Going to move on. I won't give you anything like that on the test. I just let it start at 1. But just so you know how to address that. Last one for this one, 12. You know what? Maybe I should. No, I don't want to confuse you. I was gonna start this one at 0, just so you could see that again. But n e to the n, e to the negative n. All right. So does this converge or diverge first? I see a power here. I'm thinking ratio again. So ratio, limit, n goes to infinity. Plug n plus 1 into this. N plus 1. E to the, be careful here, negative n minus 1. Let me do it this way. Yeah, no, I think I'm trying to figure out what would be the easiest to see. I'll plug it in like that. I won't distribute the negative. Over a sub n, which is n e to the negative n. And then what about the negative 1s? Well, I know that the absolute value is going to kill it off, so I'm not even worried about it. Let me try and clean this up. Limit n goes to infinity. All right, n plus 1. Now this right here, since it's negative exponent, drop it down. Since this one's negative here, I'm going to pull it up. So it's going to be n down here e to the n plus 1, and then up here e to the n. And this is limit n goes to infinity of, let's see, n plus 1 on top, e to the n, on the bottom n times e to the n times e to the 1, which is just e. These cancel. And now if I take the limit as n goes to infinity, this is infinity over infinity. I could do L'Hopital on just this. I would get a 1, and I still have an e down here. So this is 1 over e, which is less than 1. So this series converges. Let's try and get an error. I want my error to be less than 0.001. Was that it? Yeah. No, just 0.01. There we go. Now b sub n is this. And because I'm starting at 1, I don't have to worry about making any adjustments to the formula. So b sub k plus 1 would be k plus 1 e to the negative k plus 1. And I need that to be less than 0.01. So let's try k is 1. We get 2e to the negative 2, or 2 over e squared. I don't think that's going to be big enough. Is that less than 0.01? Definitely not. Let's do k is 2. If k is 2, I get 3 over e cubed. Where's my e? All right, I'm getting 0.149. That's not less than that. K is 3. I get 4 over e to the 4th. Still not good enough. This is 0.073. So k is 4. I'll just tell you. So it looks like when k is 6. Let me see. We'll go through these. K is 4. We get 5 over e to the 5th. Yeah, 0.033. K is 5. 6 over e to the 6th. .0148, still not big enough. K is 6, it's 7 over e to the 7th. There we go, 0.0063. So it looks like k is 6 will give us the approximation we want within that tolerance. All right, well, that video is gone for about 30 minutes. I'm just take a quick little break. I'll erase this and then come back in just a minute.